In this unit, we are talking about exponential functions and logarithmic functions. So we're starting with exponential functions. And so what an exponential function is a function where the variable is in the exponent. So we have some number to an x or something like that, but it has to have a variable in the exponent. Now the base has to be greater than 0. Well, and not 1, because 1 to anything is 1, 0 to anything is 0. So it has to be some number greater than 0, but not 1. So 2 to the x, 10 to the x, even 3 to the x plus 1. I can add stuff or multiply stuff to that variable. 1/2 to the x. The base can be anything that's greater than 0. Now non-examples, x squared. The variable's not in the exponent. 1 to the x. Well, that's just 1 no matter what. -1. The base can't be negative. And this is definitely a no-no. X to the x. Woo. So here we have an exponential function, f of x, equals 42.2, and then the base is 1.56 to the x. This models the average amount spent in dollars at a shopping mall after x hours. So how much is spent after 4 hours? All it's asking us to do is to find f of 4. So all we're having to do is plug in 4 for the x. Let me grab a calculator, see if we can get it on the screen. So 42.2, and you can type it in just like you see it. Now to get up into the exponent, it's this button right here. That's the to the button, to the 4th. And I get, so this is money, right, how much is spent, so 249.93. Well, what about after 3 hours? We would just replace that 4 with 3. Now, if you're reusing the same function, you can actually go up and select it and then just edit. So if you're reusing the same function over and over and plugging in, you could just do that. Or you could put it into the grapher and make a table, which is what we're going to do to make these. Actually, I'm going to do it by hand first, and then we're going to look at the calculator too, but we're going to be graphing these functions and looking at the way they behave. So I'm going to make a table. Let's just go from -2 to 2. And we're looking at powers of 2. So 2 to the -2, 2 to the -1, 2 to the 0 power, 2 to the first, 2 to the second power. Well, 2 to the 0, anything to the 0 power is 1. 2 to the first power is 2. 2 to the second power is 4, and then we'd have 8, 16, and so forth, because we're multiplying by 2 each time. When we're going backwards, we'd be dividing by 2, 4 divided by 2, 2 divided by 2, 1 divided by 2, I get 1/2. Half divided by 2, I get 1/4. So that kind of proves that idea of when we have a negative exponent, it ends up becoming a fraction. So this is the same as 1 over 2 squared. So when I graph those, I'll start in the middle. 0 goes to 1, 1 goes to 2, 2 goes to 4, 1/2, 1/4. And these are going to keep getting smaller and smaller and smaller, 1/8, 1/16, whatever, but it never actually reaches 0. So it never reaches 0. This means I have a horizontal asymptote. The graph gets really close to this imaginary line but never touches it. There's a horizontal asymptote at y equals 0. Now let's add a few other features here. What's our y-intercept? Well, when x is 0, it's 1, so 0, 1. What's our x-intercept? Well, it never touches the x-axis, so none. What would be my domain? Well, I can plug in negative x values, positive x values. This arrow means it goes on forever this way and this way. So it's all real numbers, or negative infinity to infinity. The range, remember, it can't be 0. So it's everything above that. So you could either say y is greater than 0, or we could say 0 to infinity, but notice I do not have a bracket on that 0 because we can't include 0. Now you could have done this also in the grapher. So if I go in, use a template, and do 2 to the x, we could actually use the table feature here to make that table. Now, it always starts at 0, but I could go up and select set the interval. I can tell it where to start. You could also just type in the values if you wanted. Now let's see, exact results. If I change that to exact results, look, it's actually giving me the fractions 1/2, 1/4 instead of saying 0.5, 0.25. And we can see those values. So if I do 1/2 to the x, I'm going to do the same thing, -2 to 2, but let's use the calculator to make the table this time. So I'm going to go in here, and instead of 2 for the base, I'm going to put 1/2. Whoops. Delete. 1/2 to the x. I should have just retyped it. Now let's go to the table, and I could go to the table this way or at the top, and it's filling it in for me. If I want the exact values, press that, and it gives me the fractions instead of the decimals. -2 goes to 4. Oh, because it would flip it. Okay, then -1 goes to 2, 0 goes to 1, 1/2, 1/4. It's kind of reciprocals of each other. So we get another exponential function. It's never going to reach 0. So we still have this horizontal asymptote at y equals 0. Our y-intercept is still 0, 1. Our x-intercept, there's none. Domain is still all real numbers. And the range are the y values greater than 0, but not including 0. Let's go to the next example. Graph 3 to the x, and then graph 3 to the x plus 1. So 3 to the x, three to the 0 would be 1, 3 to the first power would be 3, 3 squared would be 9, 3 to the -1 would be 1/3, 3 to the -2 would be 1/9. And again, we're going to get this same behavior. Now, what's going to happen to the graph when I add 1 to the x? Well, if we remember our transformations, adding 1 to the x moves my graph left 1. So if I have this function already graphed and I need to move it left 1, all I'm going to do is move the points 1 step to the left. The horizontal asymptote does not change. And there we go. That's g of x. Graph 2 to the x, then graph 2 to the x minus 3. So we already had done 2 to the x. This was 1, 2, 4, 1/2, 1/4. Here's 2 to the x. What's going to happen if I subtract 3 at the end? Well, when I add or subtract at the end, that moves me up or down, so this is going to go down 3 steps. So each point, I'm going to move down 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And even this half, if I move it down 1, 2, 3, I'm here, so my horizontal asymptote actually ends up moving. The horizontal asymptote is now at -3. So if I move my graph up or down, that's actually going to affect that horizontal asymptote. Now the next thing we're going to talk about is this base E. Natural base E. So sometimes we have the base of our exponential is the number E. And that is a number. If you look on your calculator, you have an e to the x, but you also have just a lowercase e. So if I just do alpha e, it knows that. It is the number 2.7182818. It goes on forever. It's called Euler's number. His name is Euler. He's famous for a lot of stuff in geometry, but he's also famous for discovering this special number. It's kind of like pi. It's a number that goes on forever, and it appears in nature. So we call it the natural base, the natural number. So we have the gray wolf population in the Great Lakes is modeled by this function, and it's the years after 1978. You'll have one on the practice that mimics this. It goes back to this same scenario. In 1960, the population had reduced to 800 wolves. They were declared endangered. So let's look at this model and see what the model says the population would be for the year 2014. So 2014 would be how many years after 1978? So 2014 minus 1978. That would be 36. So we're plugging 36 in for x. So we're plugging 36 for x. So 1145. Now if I have an exponent with the e, this button is the best one to use. So it's e to the, it already jumps you up there, 0.0325 times the x value of 36. And this model says that there were 3,689.18 wolves. Well, you can't have 0.18 wolves. But the actual population was 3,686. They made this equation in 1978. Was it a good model? Is it really mimicking that population? It is. This is a great model. Another use for exponentials is interest. How banks calculate interest. So compound interest is how banks calculate it. They calculate it on interval, either yearly, semi-annually, which would be twice a year, quarterly, which would be 4 times a year, monthly. Well, that's how credit cards get you. They do it every month. That'd be 12 times a year. So let's look at this formula. The A is my account balance. The P in the formula, that's what we call principal. It's what we start with. The R is our interest rate in decimal. And T is our time in years. The N is the number of calculations per year. Now, there is another formula for continuously compounding, but we'll get to that in a second. We're just going to practice with the compound interest formula. So quarterly compounding. Quarterly would mean the N is 4. A sum of $10,000 is invested, so that's my P. at an annual rate of 8%, change that to a decimal. Find the balance in the account after 5 years. So T is 5. So following this formula, it says P times 1 plus the rate divided by the number of calculations per year. Then this is N times T, so 4 times a year for 5 years. We're getting the total number of calculations. So if I'm calculating it 4 times a year for 5 years, that would be 20 times overall. So let's see, 10,000, parentheses 1 plus 0.08 divided by 4. On the outside of the parentheses, to the 4 times 5. And so if I do quarterly compounding, my balance is $14,859.47. What about semi-annually? Semi-annually would be N equals 2. Do you think that if I only do it twice a year, would I have more money or less money? Now you could retype the whole thing, or if you go up and select it, you can go in and edit and turn that into a 10. So notice the more times a year we compound, the more money we have. Let's see what happens when we do 12 times a year. This is what credit card companies like to do because you're owing them money. So I'm going to change it to a 12. So 10,000 times 1 plus 0.08 divided by 12. And then up here is going to be 12 times 5. So I'm just going to select, change that to a 12. And then I'm going to be kind of lazy up here. I'm just going to do 12 times 5. Ooh. $14,898.46. Now, the jump from quarterly to monthly was only $40. So, scientists and accountants and everything realize that if we went up to like 365 days, it's not going to be that much different than monthly. If we went by hours, the increase is not that different. So continuously compounding means they're compounding every second of every minute of every day over and over and over. So we have a different formula if it's continuously compounding. And this one involves E, because E is a natural number. And this is naturally occurring when we have repeated events over time. So we start with our 10,000. E to the R, which would be 0.08 times 5. A lot easier formula to work with. E to the 0.08 times 5. And I got $14,918.25. Notice it's not that much bigger than monthly. On this last one, I want you to try it. I'm going to pause the video here. You pause the video on your side, and then when you're ready, I'll show you the result. First look at this. You think compounding monthly and compounding continuously, that this would be much more money because you're compounding continuously. Because even though this is less than that percent, you think compounding continuously would give you more money in the account. The interest rate really pays, it makes a big, big, big difference. So if I calculate it at 7% monthly, I end up getting more money by $100. So continuously doesn't always give you more money. It has to be a larger interest rate as well.